looked into the regression problem. So today we will be just extending to that part and see the basic what are the problems of a regression, how do we address those problems, and further. Okay, so the machine learning approach, we need to first understand the problem and then what kind of data set that we have. Based on that data set, we extract what features to use. Then we identify whether it's a classification type of a problem or a regression type of a problem. Once we have those problems set up, then we start choosing the right kind of model. This is what the today's topic is. What is the problem with different kinds of model? And then once you have the model you have selected, we actually split the data set into train and test data set. We train on the train data set, we train our model on the training data set, and test our model on the test data set, and we look for the better accuracy or mean squared error as we saw in our tutorial section. Once we have, if we don't have the sufficient accuracy or error, um, less than certain error, then we go back again and choose redesign our model and then do this thing again. Once we have sufficient accuracy there, we deploy that model. We give that model to the user of this problem. Okay. So we looked into linear regression, where we want to fit a linear line in this data set such that this line best explains the data points. So we have this y is equal to beta naught plus b1 beta 1 x, and u is some noise, some extra residual noise, which we don't know how to model, which we have no control over this u, but what we have control over that we can actually model this data points with the line which is defined by this beta naught plus b1 x. And we found beta 1 and b1 x by simply putting it into this equation where this is equals to the mean squared error, where we want to minimize this error and then find beta 1 and beta naught, which minimizes this error. So this is what we saw last class. Okay, but what if the relationship between the variables are not linearly dependent? Say, for example, currently we are able to see that this linear line is able to best explain these data points. But what if the line is not able to explain these data points? What if we have these data points in a U shape, in a quadratic shape? So now if you try to fit a linear line there, it will not fit it properly, right? So what if the relationship between the variables are not linearly dependent? How do we identify and even a different question, how do we even identify that these linear models are not even a best fit? We can visually see such thing, but is there a proper mechanism to see whether the linear plot is best fit or not? So for to answer this question whether the linear plot is best fit or not, we actually look into the residual plots. Okay, so what residual plots is? What we do is we say that we will plot error. Y, say y is the prediction, y is the actual value, and h of x is the predicted value. That what you predicted through beta naught plus beta 1 x. So y minus beta naught plus beta 1 x. This is the predicted model, and this is the actual y. Actual y minus the prediction. You start plotting the error in it. If your model properly explains your prediction, or properly explains your y, then all your errors should be close to zero, right? If it is all close to zero, then you can say that, okay, now this model is a better linear plot. If the linear plot explains these data sets. But what if you have a data point that is like this, like your linear line is somewhere here, but your residual error points looks like U shape. Now you can say that this linear plot does not explain the data point properly because you have a very huge error at the early and towards the end. Even in between, you also have a very huge error. The gap, it is far from zero, right? The errors are far from zero and the gap is sufficiently very high. So this data point, so these data points is not well explained through your linear model. And you may want to look into non-linear models that are not linear. They are slightly non-linear models. Okay, I will stop for a while to check if this part is clear. That how do we check if a linear model is able to explain your data set or not? And for that, we use residual plots. I request everyone to ask question if they are not able to follow. Otherwise, it becomes a very monotonous thing. If you're not able to follow, please stop me there and then, because as we go for further, the topics will get more complicated. Okay. Yeah. Someone was asking something. Can you repeat what you were asking? Hello. Okay. So I'm assuming that this is okay. So this is how we do look into the residual plot. Just okay. So how do we actually once we have identified that this plot does not best once we identify that the linear does not explain the data set. For example, this is your linear model theta naught plus theta 1 x, and if x's are their data point, you can see that this linear line is not able to explain the data set. And this point, theta naught plus theta 1 x plus theta 2 x square, this explains your data really well, right? Can you say that this last one is also able to best explain the data point? Which among these three you will choose that this model best explains your data set? Plot 1, plot 2, or plot 3? Can someone say which model best explains your data point?
Plot 2.
Can you explain why did you choose plot 2? Anything intuitively, why do you think that plot 2 best explains the data point? Why not plot 3?
Plot 3 looks little overfitting and difficult to analyze, where plot 2 is little accurate to understand.
Okay. And plot 1 is simply not able to explain based on the residual plot. You will show that the residual plot of this is far from 0, but this is very close to 0. And this is also very close to 0. But you still chose plot 2 over plot 3. Okay. So you are correct though. Plot 2 is the best explains the model. And plot 3 is overfitting. As she was pointing out, it overfits the data point. What overfitting means is that the model, this blue color model, will pass through all the data points. It will try to fit all the data points, whatever data point is, even though they will make very high variance. If you look at this thing, if there is some point in between these two red lines, is my pointer visible too, right? My pointer is also visible, right?
Yes, it is. It is, sir.
Oh, okay, okay, okay. Thank you. So there is another data point in between, say if your data point is somewhere in between, you see the prediction is far from the actual value. If it is somewhere cross here, it became somewhere very far. But in this case, if the data point is close in between something, it is still able to better explain. So the point is that even though this model fits the data set, but it is far more complex. It has become far more complex. The complexity of the model has increased significantly compared to this model. Okay, so how do we make a complex model though? So one way to increase the complexity is to increase the dependency between the x's. So for example, here you see the model complexity has increased by adding a x squared term. Now you have a still theta naught plus theta 1x plus theta 2 x square. You can still learn theta 1, theta 2, theta 0 using the same mean squared error laws. but you have increased the complexity by adding a x square term. Here you have increased the complexity by adding x cube, x to the power 4 term here. You see? So that's how you can increase the complexity of the model. And this model has become extremely complex. And this model is still a good fit. This is underfitting. This is a perfect. This is a fitted model. This is a perfect fitting, and this is overfitting. It has overfit the training point. Okay, so let's actually see how do we understand overfitting. What is the implication of overfitting? What happens when your model overfits? Okay, so look at this point. Uh, will you call this blue curve or okay? So let me just first explain what is this plot is. So you have all the red dots that you see here are your data points. Okay, green curve is one of the model and blue curve is another model. Which blue or green model do you think is a good model? This blue color is a good model or a green color is a good model?
Green color.
Green color.
Okay, so you can everyone can see this, right? The green color is a better model compared to this blue model, right? So the goal is okay. So this thing, with the idea that you all are using to say that the green is a better model than the blue one, that there is this very famous idea proposed by Ozar et al. What he said was that we will always choose a simpler model that best explains the data set. We will not choose the complex model. A simpler model that best explains the data set is the one that you will be always be preferring. Okay. So what it means is, and why he says so is best explained by this. So what happens is, look at the blue curve. When your model complexity is very low, so what can be the model complexity? A straight line. If you just try to fit a straight line like this, a straight line that goes from this point till this point. It also explains the data set, but it does not best explain the data set. So the model complexity is very low, then your error can also be very high, right? Because error between the data points will be very high. But as you increase the complexity of the model, the error also starts reducing. Look at the blue point. As you made your model more complex, it is completely fitting the point. It starts going through green and you made it more complex, then it became even more blue like string. Achha, before I go there, which model do you think is more complex? Green model is more complex or blue model is more complex? Which model is more complex, green or blue?
Blue.
Okay, everyone can see this, right? The blue model, as the complexity increases, this model's variance, this kind of prediction power becomes also very, the model complexity has increased significantly. You have multiple curvatures now because the power of your x's have increased. X to the power 6, 7, 8. You have started adding x to the power 8, 9, 10. So you have started adding more curvatures now. And that's how you can say that the blue is more complex than green one. So as you increase the complexity, the error is completely close to zero now. This is the error, the blue color line in the plot is getting very close to zero. However, however, okay, let's see what happens. Uh, if you test it on other data set, okay. So remember, we always actually we have when we have a data set, we split the data set into training part and a test part, right? Remember the first instance, this one. We almost always split the data set into a training part and a test part. We keep the test data set separate. We only train in the training data set. Now you will see why we do such thing. Now, if you have the test data set separate, that test data set you have the model has never seen during training. Now, if you use that test data set to check the accuracy of the model, you will see that the green one will perform better and the blue one will start performing really poor because the error will be very high. So the test data point say maybe in between these 2 points, in between these two red points, you have your test data set here. The green will be able to perfectly explain it, but the blue model will have a very high error. So that's what will happen. The training error of as you make your model very complex, the training error will be very close to zero, but the test error will shoot up. That's what the test error will shoot up. Okay, so now what are these plots? This is a bias versus variance plot. So initially, when you were trying to explain this all these data points with a linear line, there was almost no variance at all. So there was not much like zigzag movement. All these curvatures were not there. But as you increase the model complexity, you're also increasing the variance, but the bias is becoming zero, which means the error is getting very close to zero. But when you measure your accuracy, it shows very high error. That's what variance is. So when you increase your model, your training error gets to zero, but your test error becomes very high. When your model is not even complex, when your model is very simple, your test error is also still very high. But that error is due to bias because the training error itself is very high. When your model is very close to zero, when the model is very simple, your training error itself is very high, so the test error is also high. So that's called bias. When you made your model very complex, training error becomes close to zero, but your test error is still very high, and that error is due to variance. So what you want is that you want to make your model only that much complex where your test error is minimal, very low. So it is somewhere in between. So the best model would be somewhere in between. It's neither very less complex or neither it is very complex. Nor it is a low complex model, neither it is very high complex model. Somewhere in between is the model that you prefer. Okay, I will stop here to see if there are any other doubts. I want you to take away from this plot is that as the model complexity increases, the training error goes to zero, but the test error will shoot up very high. Simply because now you have made your model so complex that it is not able to explain certain data points. It has more curvatures to fit all the data points. But if a point comes here, it has very high error. So you need to choose a model which is in between, which is neither very complex nor very not even complex at all. I will. Can someone confirm that they are able to follow this part, or if anyone has any doubt there, if they are not able to follow this plot, I am happy to repeat again. So
Can you explain the variance again, sir?
okay. So so there are two kinds of error. Why there is a very high error when the model is your model is not even complex, when your model complexity is very low, then your training error would be also be very high. Why I say a training error is high? Say for example, your model is a straight line. You fit a straight line like this, a straight line. Okay. Now, if you fit a straight line, you can see that this point is here, but your prediction is somewhere above a straight line. Let me see if I can draw something. Uh, can I draw the way? Okay, let me see. Okay. So say for example, you have this is your model. Okay, the black color that I have drawn. This is the very low complex model, and this is what it was explaining. Assume it. Now you see that your one training point is here, but your prediction is somewhere here, right? This is your prediction. So you see the error is also very high, right? Such a large error. Here, this is what you have predicted, and this is what your actual point was. So the error is also very high, right? You can see, right? Okay, so when your model is is of low complexity, your training error is also high, and your test error will also be high. Say, for example, your test points are here. So let me just choose a different color. Say test point I should choose with green. Alright, it made everything. Okay, how do I do? Just choose this highlighter. I don't know what it will highlight. Say your test points are here. Okay, so this is, say this is green. Oh, say your test points are here. All these green lines that I am trying to draw, these green boxes are your test points. Say all these are test points. So even in the test points too, the error is also very high. Why is it? So between these points, the prediction and the actual one, the test error is also very. So when your model is very little less complex, low complex, your training error and test error is very high. The student who asks this question, is this part clear? When your model is very low, less complex or low complex, your training error and test error is very high, right? This is your training error because the data point was there, training error, and this is your test error. This, ah, this is so difficult to draw. So when your model is less complex, your training error and test error both are high. That's because of your model is very less complex at all. That's what we call biased error. Now the variance error increases. There you don't have variance error. That's because of bias error because your model is almost no there is no complexity in the model itself. Okay, so this is due to that. Now let's look into when you have this. Delete all this. Okay. Now let's look into when your model is complex. When your model becomes complex. Say your model is very complex, like literally very complex. So something like zigzag thing has happened now. Or it has training error is close to zero because it best have started fitting all the training data points. Wherever is the prediction value and whatever is the actual value, they are all equal. So training error is close to zero. Now test error, if you see, so say your test point is here. You see, your prediction is here, but the actual real value is here. So the test error is very high. You see, the test error points are so high. Your training error goes to zero, but test error still is very high because your model has become complex. That's what we call variance is high. This error is due to variance. Where your test and train error both are high, that's due to bias. Your model is not even complex enough. When your train error is close to zero, but then do you see a test error is also very high, you call it that error is due to variance because it has very high variance. You see, around a data point, you see a very high variance. Multiple curvatures are there. Is this clear? The
Yes, sir.
student who asked. Okay,
Yes, sir.
okay. Thank you again. Uh, So I'll tell you everything. Okay. So one last time, when your model is very less complex or low complexity, both your training error and test error will be very high. When your model is very complex, your training error will be close to zero, but your test error will still be very high. That's why we need a test data set to understand whether your model that you have trained, whether it will perform good on unseen data set or not. Because anyways, you want to use this model in real world setting, and the data that you will be feeding in this model would be a new data point, which your training set does not have. That's why we need to check whether your model is overly complex. If it is overly complex, that is the test error will be very high and train error will be close to zero. And if it is very low complexity model, then the train and test both will be very high, which is easy to identify. What you need to find is a model that is in between, and that's why we need a regularization, that we don't know what level of model complexity should we introduce. Say, for example, should we introduce x to the power 4, or should we include x to the power 10, or should we include x to the power 100? These data points are very easy to visualize because you can plot these data point in a 1D graph, in a 2D plot. So this x-axis and y-axis. Maybe on 3D plot you can plot x-axis, y-axis, and z-axis. In those plots you may also be able to plot. But what if your data point is very large? There are like multiple x's. Say x, y. Remember the diabetes data set? It has size, age, some S1 to S6 number of features. So many features are there. How will you even visualize such thing? So how will you, if I start including S1 square, all those features, squares, those terms, so the model can become extremely complex. But where should we stop? So for that we use regularization. Okay. How do we avoid overfitting? So one way is you can manually select all these things, whether we should choose x to the power 4, x to the power 2. One thing you can do is manually select and then do model selection and modeling. The other thing that we do, the most of the time we do, is regularization. We rarely select manually that x to the power 4 fits the best or x to the power 3 fits the best. We rarely do such thing. Most of the time we use regularization. What does this mean is keeps all the features but reduces the magnitude and the value of the parameter. So what it does is that it keeps all these values, all theta 1 to theta 4, but it reduces the weights of these values. So in general, it will try to reduce the weights of these values so that it does not become overly complex. So you will see what it does though. Okay, so there are two types of regularization that we will be studying. One is ridge and another one is lasso. So if you look at this is what our prediction model was, linear model. Uh, Xij is the data point and Wj is your beta 1, beta not 2, beta m. So Wj, think of it as betas, and Yi is your true value. This is your predicted value. The square of that you want to minimize. Initially, you are just minimizing this. Now you have added this term too. So you want Wij whole square. You also want to minimize this. So basically, if you just minimize this, you are asking that all the Wj's should be small or close to zero. So you are trying to decrease the weights of all the Wj's. So you want to decrease the value of all the Wj's in it. Okay. So once you decrease the weight of it, you see how it is going to affect. This is one where you decrease the weight of the Wj's by using a square of the Wj's. The other way to decrease the weight is just add a mod of wj's. Okay, if you just add mod of wj's, so you will see what happens with the behavior of ridge and lasso. Okay, and you weight this term, that how much you want to give weight to regularization and how much weight you want to give to this lambda controls. If lambda is very small, very close to zero, then you are not doing any regularization. If lambda is equal to zero, then you are not doing any regularization. You can simply remove this term and you only have this term. It's the without regularization. Now, if lambda is very high, maybe close to infinity, so you can see that if it is close to infinity, so this term becomes zero. So you are only regularizing. So if you do it, lambda is infinity, and you multiply all the term by 1 by lambda. So you see 1 by lambda, 1 by infinity is equal to 0. So this term will become 0 and this term is 1. So everything, you are only doing regularization. You are not even doing model fitting. So when regularization is very high, so you are putting everything should be close to 0. So Wij's all will become 0. So lambda controls how much regularization you want to do, whether you want to put a very high regularization or a very low regularization. So if you put lambda equal to 0, you will make your model literally not, you will not be doing any regularization. If you can put lambda equal to very large, you will make your model complexity close to 0, like very low complex. So if you put lambda equal to 0, model become very high complex. If you put lambda equal to 1000 or a very large value, you make it your model complexity close to 0. There is very low model complexity. Okay, so let's look into what happens with each of these things. When lambda is equal to 0, the model is very complex. Look at this thing. The blue line is the model true function. This is the actual function, and dots are the data points. So you see that if the lambda is equal to 0, your model is very complex. There are multiple curvatures and it is fitting all the training data points, close to all training data points. But when you set lambda equal to 0.5, which you are slowly, no, let's not look into lambda equal to 0.5. Let's look into lambda equals to 1000. When you put such a very large lambda, what you made your model is very low complex, just trying to fit a linear line. And this is how it starts to fit. You see? Now you don't need whether you should choose 10 to the power x, how much complex model you should choose. Now you don't need to choose the model complexity. You just need to tune lambda. How much lambda you should choose so that your model becomes properly fit. So you choose a very complex model, like this is the very complex model, and add a regularization term. If your lambda is very close to 0, your model is very complex. And if lambda is very high, that means you made your model very simple, low complexity. It becomes a straight line. But if you choose anything in between 0 and a very large number, your model have started to explain your data set now. Look, the model is now becoming, the blue color line is starting to explain the data points. If you increase these data points, the true function, even better. So lambda now controls your model complexity, basically. Now you don't have to worry about this thing, that whether you should stop at x to the power 7, x to the power 10, x to the power 100, or whatever you want to choose. Choose a very complex model like x to the power 200. Go till x to the power 200 and add a regularization term, either a rigid regularization or a lasso regularization. Add whatever regularization you choose, and you can control that regularization through lambda. So you can play with lambda and see which lambda fits the dataset properly. And you can see the training error. When your model is very complex, your training error is close to 0, 4.99 e to the power minus 3, which is 10 to the power minus 3. Whenever there you see e, read it as 10 to the power minus 3. So it's very close to 0, but the test error is very high. See, 1 into 10 to the power 1. So which is, the error is 10. So your training error is close to 0, but your test error is 10. So you can see that this is because the model is very complex. Here, you see the training and test error, both are close to 0. 10 to the power minus 2, so which is 0.07, 0.06. So train and test error are very close to each other, which is a good model. Here, the model has become so simple that the train and test error both are high, 0.4 and 0.4. These are all, assuming here 10 to the power minus 1, it's high though. I think this number is slightly not correct. It is supposed to be not minus but something else. But the numbers are sufficiently high. This number is not so correct. But here the training and test error both are high. The best model is this, where training and test error both are low. This here too, the train error is close to 0, but test error is very high. That means the model is very complex. Here, the model is very simple. So you need to choose something in between. And lambda controls the weight, what model that you are planning to choose. Okay. So that's what it is. Where you have low regularization, the model becomes very complex, and the error is also somewhere in between. When your lambda is very high, your model becomes very simple, and your error again becomes very high. Okay, so that's what it is. Higher lambda means that uh, model becomes very low complexes, and the lower lambda means your model becomes very high complex. And you need to choose lambda for your own data set. Whichever data points you have, more or less lambda becomes a hyperparameter. You tune that hyperparameter, you tune that lambda value appropriately for your own data points. Okay, till this point, do anyone have any doubt how lambda is able to control the model fitting part? So this part. So we will see more of such example in our tutorial. What is the effect of using this regularization over this regularization? But given that there is a lambda controls this model complexity, do any of your students have any doubt regarding this?
Clear, sir.
Okay, thank you. Okay, so we will see these things again. Let's just go through this. Ridge regression. Okay, so let's not go over this. We will come back to this slide again when we do this tutorial. So this is the difference between ridge and lasso. When ridge works and when lasso works. But since you need to see ridge and lasso in visualization in tutorial to actually see when ridge works and when lasso works, and how is this ridge regression, the square term, and lasso the mod term, how are they different and what kind of effects they bring. We will see this thing in more tutorial, and then we will come back to this slide again. Okay, so the other question is, so remember that we have everything that we did was, we have the data set and we split the data set into train set and a test set. Test set was used to check whether your model has become very complex or whether your model is very simple. What is the state of your model? And you need to find the best model that best explains your data. So that was what we were using for test set. But what if we have the data set itself is so small that we do not have enough test data points? Say, for example, we only have 10 data points. Now, if you train, how will you choose a test set in this? You have so small training set. You can't test on such a, say, in this 10 data points, if you choose 2 data points as test set and 8 data points as train set, in just 2 data points, you can't even say whether your model is correct or not. It can be just be some random data points, which says that your model is very good. So 2 is so small that you can't even say it correctly, appropriately. So what we do in such case is we use the idea of cross validation. So cross validation, when your test set is so small that you cannot actually measure your model complexity or model error properly, you use cross validation there. So the idea is very simple. Let's go to the idea itself. So what you do is you first, this is your total number of data points, 1, 2, 3, 4, and 5. Say assume you have total of 5 data points. There is no other data point available. So what you do is you choose 4 of these as a training data points and one of this as a test data point. Okay. You train your model in these 4 data points and then test on this test data point. You will have some error. You report that error as error 1. This is the error that you got while after training on this 4 data set and testing on this data set. This is error 1. But this error 1 is not sufficient because you are only testing on one data point. This one data point may not be sufficient to tell you that your model is very poor. Say, for example, let's take this example itself. So you have trained on so many data points. What if the test data point is close to here, this dot? It will say that oh, your training test error is also close to 0. But as you have seen that if you measure it properly on a proper large amount of test data points, your test error is very high. So you cannot just rely on just one single test data point to tell that your error is low. So this is the problem. You cannot say that error 1 is your error of this model. So what you do is second time you make your test data set as this point, this gray color box in the iteration number 2, and you have 4 data points here. You train on these 4 data points and report your error in this. So this will give you error 2. And similarly, you run for all data points. You make all data points at once, all the data points as the part of test set and train on the remaining. And then you will have 5 different errors, and then you report the average of these 5 errors. This will ensure that you have measured when if your model is truly accurate or not. Most of the time we use cross validation when our test data set is very small to make sure that our model is a good model. Okay, in all these iteration, when you do iteration 1, you train only on these 4 and test on this. In iteration 2, you start from scratch. You train only on these 4 data points and test on this and report the error 2. In training iteration 3, you again train from scratch on these 4 blue colored boxes training set and report your error in this gray color box. Similarly for iteration 4 and 5, and after that, when you have to report your test error, what is your error of your model? You do an average of all the 5 and report this is your error. Okay. Hmm. Does this make sense? That when your test set is very small, you use cross validation there. And then you calculate that every iteration you calculate the error on the test set, and all the iterations that you have done, all the iterations error, you take an average of that and report that is the error of your test error of your model. So what we always need is the test error to make sure that whether how good your model performs on an unseen data point. That model has never seen how good your model performs on this unseen data point. Okay. Any doubts till this point?
Sir, in cross validation, how
Uh-huh.
do we focus on the error during the training data set?
Okay. So let me actually give an example though. Let me actually draw an example and see if I can draw something. Okay. So let's see if I can draw something. Okay. So let me draw a thinking system. Okay. So say your training points are here. So say only three data points are there. Forget about 5, 7, 10. Only three data points are there.
Okay.
Okay. So what you do is that you keep first you keep this as test point. You only train on these two data points. So say your model is very complex. You did this. It will learn this function. Okay. So this is the function that it has learned.
Okay.
Okay. And you report your test error. This is your test error. Right. This is what you have predicted, and this is what it is. So difference between that is your error one. Right. Is this is this part is okay?
Yes, sir. And then similarly, we'll choose the other 2 points and give
Wait, I
select
will come.
one
I will
area.
come.
Okay.
I will come. So this part is okay, right? This is the error one. Okay.
Okay, sir.
Now, now let's go into other part now. So let me delete this section now. Okay. So you have this is this one, and this other one. Now you consider this as your test set. Now you start fitting a model here, and this is how you have done. Okay. Say this is what you have done. Now your error is this point. You know why the previous curve and this curve looks different? The question you might all be thinking, why is this curve
Yes.
and the previous curves look different, right? This is the question that is coming to your mind, right?
Because we are making a quite accurate and a complex model.
Yeah, because this in the first case you had access to this data point, so you ended up actually using that data point. But in the second iteration, you don't know this data point, so your model is only training on this point and this point, only these 2 points. So it does not have access to this data point. So it ended up finding an error of this much, right? Okay, let me actually make it even more diverse. Let's redo this example. Wait a sec. Let me do it even more. Uh, it will make clarity even better. Wait a sec. Let's just do this thing. So you have 3 points. Let's go back to iteration one. We are doing this is your test data set. Your model is extremely complex. Okay. So what you do, this is how you will look like. Say you fits it and okay, sorry, fits it again. So this is your data point and this is your data point. Okay. So your error is this very high. So this is your E1. Okay. Now let's do E2. Okay. Let's make this as your test point and this is your training point. So now it will start fitting this curve. Say this as fit. So our E2 is this very large value, right? E2 is this, and E1 was the previous one. Both E2 and E1 are very large values. Can you see this part at least? Both E1 and E2 were very large.
Yes.
Okay. Now, let's not do iteration 3, 4, and 5. Okay, let's do it one more iteration. Iteration 3 is only needed. Okay, let's do iteration 3 too. Okay, let's do iteration 3. Okay, let's do iteration 3. So now this is your test point. So your model will start fitting this. Somewhere it goes. So your error is this value. So your E3 is also very high. E3, E2, and E1. Both are very high, right? All three are very high. Can you see? Hello?
Yes, sir, we can see that.
Okay. So now when you actually report the average, you will see that the test error is very high. If you just average all these terms, all are very high value, you will report a high error. Now see that what is the problem, which is correct. This model is so complex, the test error should be very high, right? Since your model is very complex, it has ended up actually not learning the good function, but it ended up learning a very high noisy function or a very complex function. But what if you have not done this thing? If you have not done this thing, this is what you would have ended up doing. Say, uh, if you have trained on all the data point, it would have ended up doing this thing. Since it's a very complex model, it would have ended up actually learning everything, and it would you have reported training error is close to zero, and test error. There were no test points since you did not do any testing. But what if you have chosen only one iteration one? There was no other iterations. If you have chosen only iteration number one, if you have chosen only iteration one, so this was the first learning that has happened. Sorry, this was the first model where error was this such high. So your error one initially could look like a very small error, but actually on an average, if you do all three errors, the error would be very high. If you have only done iteration one, you may get lucky and you see that the error can be small, but your model is so complex that it should have a very high error. You should be able to see high error, but when you do cross validation, you were able to find that your model is very complex and it has high error. But if you have only done iteration one, this is just choose any test point randomly. You are not able to see. You may get lucky to see that your test error is high, but in general you will end up finding that you may get sometime unlucky to find a test point which will say that it has very low error, but actually the model would be very complex. So that's why you do this three-way the cross validation to make sure you are accurately able to capture your model's true test error. We will see this thing in tutorial again. So
Okay,
this
sir.
thing helps us to understand how to capture the test error accurately. When your data test set is very small, just by choosing any random test set and reporting your error there, you may report an incorrect value, not the true
Understood, sir. Huh.
representative value. But when you report it on multiple iteration and then average it, you will report the actual correct value. That's why we do cross validation. In general, cross validation can be used in any test set. Even when your test set is sufficiently large, you can still do cross validation. But when your test set is sufficiently large, cross validation will also report similar answer, as your single iteration would have reported because your test set is sufficiently large. But if your test set is very small, your tests you need this cross validation. Otherwise, a single iteration may report a erroneous error. This error value that you will report will be an incorrect value. That's why we need cross validation. The more we will see in the tutorial section, and yeah, that's what we have for today. Uh, I think I ended up taking another 6 minutes more, but yeah. So yeah, this is what we have for today. So we will see all these things in tomorrow's tutorial. So we will see ridge and lasso to how to control model complexity and the cross validation part. What happens when we just report on a single iteration test set, and we'll see that the error becomes like random. It will report that you are very good. The error will be very small in iteration 1, and in iteration 2, iteration 3, when you do iteration 2 and iteration 3, you will see that the error is very high. So the actual should be very high, but since you chose only one iteration, you ended up reporting that the error test error is so small you can use this model, but which was incorrect. So we will see cross validation in tutorial and rich and lasso in tomorrow's tutorial. Yeah, that's all for today. Let me share the PDF with you. One second. Okay. So can someone confirm if you are able to see the slides?
Yes, sir, we are able to see.
Okay. Thank you again. Thank you so much. We will see tomorrow's lecture. We will be see tomorrow's tutorial. We will see regularization and cross validation thing. Thank you again. We can end the lecture though.